Okay. Can I make the same silly request that you give me a watch? Or a Thank you. Okay, so I told you yesterday that Fuchs, Runkel and Schweigert have a construction that takes as input a chiral conformal field theory and a Frobenius algebra object in the category associated to the chiral conformal field theory, and that using those two inputs, they produce a full conformal field theory. So this is a big body of work, and I'm not going to be able to reproduce the whole thing here. But I want to tell you at least how to, well, given a chiral conformal field theory and a Frobenius algebra, how to get the value of the corresponding conformal field theory on a closed surface. This is called the partition function. That's the value of the partition function on that closed surface. And that's now a number. And that's what I'm going to explain. So in particular, we have this. So the first thing that these guys do is to draw the following picture. So let me explain a bit what that picture is. So this is a picture of a three-manifold, namely the three-manifold sigma cross the interval 0, 1. And well, this is sigma cross 1. This is sigma cross 0. And in the middle, you have sigma cross 1/2. We're actually not going to draw sigma cross 1/2 in this three-manifold. We're only going to consider a ribbon graph that is on the surface of sigma cross 1/2. So this is a so a ribbon graph is an embedded graph which is a little bit thick. It's a two-dimensional little thin thing. It's a little thin ribbon. In this case, it has trivalent junctures. This ribbon graph is oriented. I haven't drawn it here, but each one of these pieces sort of knows in which direction it goes. And at the trivalent junctures, you either see 2 incoming, 1 outgoing, or 1 incoming, 2 outgoing. It's possible to make choices of orientation so that always happens. And then this ribbon graph is labeled by the Frobenius algebra object. So if I have a piece of ribbon that's there, then that is, so the Frobenius algebra was called Q. So this is labeled by Q, and it has an orientation, so here. And if I have a juncture like this, where sort of goes this way, then this is labeled by the multiplication morphism, which goes from Q tensor Q to Q. And if I have a thing which goes in the other direction, this is labeled by the co-multiplication, which goes from Q to Q tensor Q. OK, so this is the kind of thing that this is what this picture means. It's a labeled, embedded trivalent ribbon graph. OK, so no, the complex structure on the surface will orient this big ambient 3-manifold. But these are just arbitrary choices. Just like the ribbon graph itself. I mean, you want eventually this number to not depend on the choice of ribbon graph. But before I tell you more about this picture, let's first think a bit about what the chiral CFT does to sigma. So I projected this slide that you have already seen before. OK, here's sigma. It happens to not have any boundary. Associated to sigma, we have a functor from the incoming category to the outgoing category, meaning from the category associated to this boundary to the category associated to that boundary. But those two boundaries are empty. And therefore, we need to think about what is the category associated to the empty one manifold. And in any chiral conformal field theory, that category is just a category of vector spaces. It's the trivial thing, which in this case, trivial means vector spaces. Let's see. I need like this. So we have associated to sigma a functor from C in to C out, but I told you that that is just vect, the category of vector spaces, and that is also vect. And such a functor, I should have said these are linear functors, such a functor is entirely determined by where it sends the one-dimensional vector space C. C goes to something, and once you know that C goes to something, you know that C squared goes to twice that thing, and C cubed goes to 3 times that thing. More generally, a random vector space X will go to X tensor, the image of C under the functor. So any functor is of the form X goes to X tensor V. And providing a functor from vect to vect is the same thing as providing a vector space. This vector space has a name. This vector space is called the space of conformal blocks associated by the chiral CFT to the surface. So this is well, that's just terminology. OK, so what next? So this was this line here. Let's look at that. So now we have, so I claim that there's also a canonical element in that vector space V. So what does this thing say? It says that for any element in the category C in, but we already know that C in is vector spaces, and probably the only interesting element to take is just C itself. So let's think of C being the complex numbers, and this is the category of vector spaces. So associated to the complex numbers, we have a map from H sub lambda to H sub f of lambda. So this is f. So let's write it like that. So we have H sub lambda goes to H sub f of lambda. But lambda, we took that to be C, and H sub lambda is also C. Well, the image of lambda under f is V. So this is just another name for V. And a map from C to V is the same thing as the data of a vector. So 1 living in C maps a vector. Let me call it little omega. So the data of a chiral CFT produces for you a vector space, namely the space of conformal blocks, along with an element omega in that vector space. So we have V, and then we have omega, element of V. So in order to assign a number to sigma, what Fuchs, Runkel and Schweigert do is they invoke the existence of a three-dimensional topological quantum field theory that is able to take as input such a three-manifold with boundary. And it's a TQFT that actually can take as input three manifolds with stuff in it. And in particular, those things are things that it can take as input. So the 3D TQFT assigns to such a thing a vector in the space of conformal blocks associated to the boundary. So assigned to so what is that? That's two copies of V. More precisely, one of them has one orientation, the other one has the other orientation. So it's V tensor V dual. V tensor V with the other complex, sorry, V tensor V complex conjugate. So we have, let's call that element, so we have omega in V from this story, and we have, let's call it C in V tensor V dual, complex conjugate. These are Hilbert spaces, so it doesn't really matter. But anyways, this is what we have. And well, how do I do something with that data? Then the answer is it's what you get if you pair those two things together. So omega tensor omega bar, that's the canonical thing that lives inside the conformal blocks of this, paired with that element that's given to you by the three manifold. Okay, so that's, I haven't told you what the 3D TQFT is, but that at least it gives you an idea of the ingredients.
Sorry.
Yes?
Quickly remind me why C in and C out are vect. We assume, I just don't remember.
Okay. A quantum field theory is a multiplicative assignment. It takes in manifolds and produces stuff, either numbers or vector spaces or categories, depending on what exactly the dimension of the manifold is and what exact kind of quantum field theory you have. But it always is multiplicative, meaning it sends a disjoint of manifolds to tensor products of, or products of whatever algebraic things you have. So the product of numbers is just the usual product with unit 1. The product of vector spaces is tensor product with unit the complex numbers. The product of categories is a bit more fancy, and it has a unit, and that unit is the category of vector spaces. So, so that's why, because the manifold is empty, you're forced to put the unit for whatever notion of tensor product you have on your things.
So maybe you can say, a bit more details, what kind of categories you consider here? Is this C-linear categories?
Yes. So for the kind of CFTs that we're looking at here. These are going to be categories that look like a finite direct sum of copies of vect. So they're semi-simple, finitely many simple objects.
And you don't have a tensor product in them?
This assignment does not, this assignment on the top eats one manifold and produces a category, no tensor structure. This assignment endows the category with a tensor structure. Namely, you have the pair of pants that will go to a functor, and therefore you see that the category actually has a, well, it's more than just a tensor category, it's a braided tensor category. So I've set up things in such a way that the fact that it's braided comes after the fact, if you unravel a bit the definition. But yeah. You need the tensor structure in order to make sense of what the Frobenius algebra object is. So that. Okay. So that's the partition function. The next question is what is the state space of the CFT? In other words, what is the Hilbert space that the CFT assigns to a circle? That's called the state space. So for that, one considers the same picture as above, but we're going to introduce a boundary in this manifold sigma, and try to think about how to make this picture consistent in the presence of the boundary. So here, let me erase a little bit of the manifold and put a boundary. And I'll do the same thing below. So I erase a bit of the manifold and I put a boundary. And so we're still going to do sigma across the interval. So actually I've removed the whole cylinder. Okay. And now we need to think about how to make sense of this. And it turns out that, and I'm sort of skipping a few steps, that then rather than considering this tube that goes in there, we're going to consider a ribbon, just like one of those, that goes from the top into this network here and from the bottom also. And we're going to try to ask, like, what is the most reasonable value that one can assign to this ribbon? So let's draw that. So one has this network, which I've been drawing in green. So let me continue drawing it in green. This is a piece of it. That's one of the ribbons. It continues. And we have another ribbon that comes from above that lands on it, and one that comes from below. And the question is, if we're going to assign Q here and there, what is the universal way of giving an assignment, of assigning a value to these guys? So we need some compatibility between the fact that we're allowed to move this network arbitrarily. By the way, I should have said the fact that Q is a Frobenius algebra is exactly what tells you that it doesn't matter if you can sort of, like, if you do these sort of local operations of, like, replacing, say, the network. This you can replace by, say, by that. One of the Frobenius algebra axioms says that the composition of multiplication with co-multiplication is the same thing as a composition of, well, here co-multiply and then multiply there. So all these moves allow you to go from any one of those to any other ones. But now we need to have compatibility between those kinds of things and the fact that we have stuff coming from above and from below. And let me draw the compatibilities that one needs to have. So here's one of them. So if I pass one of these junctures across this place where the thing happens, I should get the same value, and or the same morphism in the category C, and similarly for something happening from the other side. So we're looking for a universal way of assigning a value to those orange guys so that these equations are satisfied. So, well, you might guess that what we want is two objects, one in C and then again another in C. But actually what one wants is one object in the tensor product of two copies of C. And the object that's universal with respect to those requirements is called the full center of the Frobenius algebra. And it's a little bit of an ugly expression. It's a direct sum over all, well, pick one irreducible object of each kind. So it's a direct sum of all those of Hom as QQ bimodules from lambda, tensor from above Q, tensor from below with the dual of mu into Q, that's another bimodule, all that tensor lambda and tensor mu viewed as an element of the second. So this is an element of C, a tensor product with the complex conjugate of C. Okay, so this is something that Fuchs, Runkel and Schweigert write down, and they prove lots of good properties about that, and that's a way of justifying that big formula. This is not quite the state space. The state space is not an element of this abstract category. The state space of the CFT is a Hilbert space. So here, the state space so this is called the full center of Q, and the state space of the full CFT associated to to a chiral CFT and Q, a Frobenius algebra object, to Q is and H full is the direct sum lambda mu irreducible object of C, Hom QQ, lambda, tensor from above Q, tensor from below duo of mu Q times H lambda times H mu bar. So let me comment a bit on all these things. First of all, I sort of maybe didn't emphasize it, but I said it en passant, which is that the category C, this category there, is a braided monoidal category. And in a braided monoidal category, and in a monoidal category, you can tensor things from the right or from the left. In a braided monoidal category, you can tensor things from the right, from above, from the left, from below, from any angle you want. So this means that I take Q and I stack a copy of lambda on top of it and a copy of mu on the bottom.
Can you say how that works? Yeah, the tensor from above.
It's a bit tricky because all these tensor products are isomorphic. But one way of thinking of a braided monoidal category is to say that I have operations. So I have an operation from C times n copies into C for every picture of the kind that I'm about to draw. And boxes that are sitting in a big box. So we have one such operation for any one of those. And they're required to be compatible in the sense that if you take one of these operations and compose with another such operation, that it is reflected by the geometry of these little boxes. Like you redraw the picture inside the box, and that's the new operation. Well, here you have too many operations, clearly. Have like an uncountable number of operations, one for every such picture, so I need to cut it down to say that I actually have fewer. And whenever you have a homotopy between such a picture and another similar picture, another picture with the same number of boxes, you want a natural transformation that says that relates those two operations, that equates those two things.
That's like that homotopy is like the braid.
That's right. So for example, there is a homotopy between this picture and that picture. Oh, these are they're numbered, 1, 2, 3. So there's a homotopy between this picture and that picture that goes like that, and there's another one that goes like that, and those two homotopies correspond to different natural transformations between the multiplication map and the opposite of the multiplication map, the map that's like first exchange and then multiply. These are like the left and right braidings. So if you adopt that picture, then you can also tensor from above, just like you can tensor from left and right. So that's what I'm doing here. It's convenient to think of it that way, because then this thing is a bimodule. So here, Q is in the middle, lambda is on top, and mu is on the bottom. And I need two actions of Q. Well, these are the left and right actions of Q. So lambda and mu sort of leave space for Q to be acting. If you don't adopt that picture, it's sort of difficult to say what that thing is. Q is a bimodule over itself in the natural way. And then you look at Homs in the world of QQ bimodules. That's just a vector space. This is just a vector space. It's a finite dimensional vector space, just like here, the same vector space. Well, lambda is an element of C. Mu bar is an element of C bar. So that's an object of C tensor C bar. Here, it's the same picture, except that this is now a Hilbert space, and that's a Hilbert space, and the result is a Hilbert space. Not an element of this category, but a concrete Hilbert space.
And is this a Hilbert space assigned to? I kind of got lost in that. the way.
Yeah, state space means
Circle.
the Hilbert space that the full CFT assigns to a circle.
Right.
So,
This circle was on this particular surface.
yeah. So
Why did you need that if you wanted to mean that sort of you're assigning to sort of an abstract circle?
well, let's see. There's this is just a little bit of how this should interact with this previous thing, and I really haven't spelled out everything, and I cannot do it now. I'm just sort of okay. What I wanted to do is to have this formula on the board, and I wanted to give it with some justification at least, and well, I've given some justification. I should also say that my main goal is to produce an example of one of these extended conformal field theories, and I won't be able to construct the whole thing. I'll construct some parts of it, and then at some point you need some way of checking that what you've done agrees with what other people expect to happen. And this is going to be my check. I'm going to say, okay, I'm going to assign this von Neumann algebra to the point, and you'll be like, why? And I'll be like, believe me, that's the von Neumann algebra that you want to assign to a point. And then I'm going to say, I'm going to assign this bimodule to an interval, and you'll be like, why on earth? And I'll be like, believe this is what you want to do. And then I'll take two intervals and I'll glue them like that, which means I take the confusion of, well, this viewed as a left module and that viewed as a right module, and you'll get a Hilbert space. And then I'll produce a canonical isomorphism between this thing and that. And then you're like, okay, indeed it agrees with what people expect. So that's why I want to have this picture there. But I should say, I strongly recommend reading what Fuchs, Runkel, and Schweigert have done. I mean, it's very nice work. It's very readable. It's also lots of pages, but that somehow goes together. If you explain things smoothly, it ends up taking time to write it. Okay, so there's one feature of the Fuchs-Runkel-Schweigert construction, which is that if I change the Frobenius algebra and replace it by another one which is Morita equivalent, maybe I should say what that means. So two algebras A and B are Morita equivalent if there exist bimodules, an AB bimodule that I call X, and a BA bimodule that I call Y, such that X tensor with Y over B is isomorphic to A as an AA bimodule, and similarly Y tensor X is isomorphic to B as a BB bimodule. That's the usual notion of Morita equivalence. Now, all these things are objects in the tensor category C, so you need to make sure you understand what it means to tensor an object with another object over an algebra object. So this is defined as some kind of co-equalizer of. Anyways, this is it looks just like the definition in algebra, except you need to interpret it inside C. So if I take Q and change it and replace it by another algebra which is Morita equivalent to it, well, this picture changes, of course, but this full center is the same. And so two physicists, Kapustin and Saulinas, recently gave a very nice way of reinterpreting that fact. So recall that so one of the rules that I had listed was the following. It said that if I first co-multiply and then multiply the result, that should be the same thing as doing nothing. So this is this thing that's like not always included in the definition of a Frobenius algebra, and if you include it, that's called a special Frobenius algebra. Certainly something you want if you want this to be invariant under any kind of transformations. I mean, you want things like that to produce the same answer. Well, so if you think about this, what is this? This is the operation of plugging in a hole. You take that hole and fill the hole. So this says that whenever I see a hole, I can fill it in. So let's start filling in holes. So for example, here's a hole. I could have replaced it by a thing which is filled, and I won't see a difference. Similarly, here I can replace it by a thing which is filled, and if you do it everywhere, then what you see is the following picture. It's again sigma cross I, sigma cross an interval, but it has in the middle an embedded surface. And this surface should be decorated by a so-called defect. Defect is also called a domain wall. It's also called a surface operator, but let's call it a defect. And they argue, so Kapusin and Salina argue, that the defect only depends on the Morita equivalence class of Q. Whereas in order to interpret this, you need Q itself. In order to interpret that, you only need its Morita equivalence class. And they go one step further and say, well, you can actually...
What is the defect?
Sorry?
What does it mean to decorate by a defect?
Well, it means the same thing as to decorate this thing by a Frobenius algebra. It means that there is a notion of what a defect is, and you label this by that defect. And then the notion of what a defect is should be made in such a way that it is possible, using an extension of the 3D TQFT formalism, to do the same things that you knew how to do when you had graphs. I mean, I haven't told you what a defect is yet. And Kapusin and Saulina also don't say what a defect is. They just postulate that there exists a sort of physical notion of defect, and then that it does what you want. They also say that, which is a very neat thing, that these ribbons can actually be taken seriously as actual little ribbons having a little piece of two-dimensional surface labeled by this defect, and the stuff that's drawn in green here, that is the thing which is labeled by the Frobenius algebra. So, and then the idea is you can like punch holes as many as you want and like label the boundary of the hole by Frobenius algebras in the Morita equivalence class of this defect. So far, what I've described to you is what other people have done. And I would like now to prepare the ground for the construction that of extended CFT. So I might have told you earlier, but let me remind you, the formalism for chiral conformal field theory that I'll take as the beginning point of my construction is that of conformal nets. And I promised you yesterday a definition. And here is, let's see, I hope this is readable. I need to make it a little bit smaller. Oh, it goes all the way up. That's sort of, let's see. I think I have everything on this slide. So let me comment. Hope this is readable. So a conformal net is a functor from, so yesterday I had put here the category of all compact one-dimensional manifolds. It turns out that it's easier to put only contractible one-manifolds in the definition and to say that the value of the remaining manifolds are derived from those. Everything is determined by those. So we have only things that look like an interval. To an interval, I assign a Von-Neumann algebra. To an embedding of intervals, depending on whether this embedding is orientation preserving or orientation reversing, you assign either a homomorphism or an anti-homomorphism. This assignment should be continuous, so there's a topology of the Hom sets between intervals, namely the C infinity topology. There's a topology on the Hom set between Von-Neumann algebras, the Hagerup U topology. I won't tell you what that is. This assignment should be continuous. The first axiom, I had already mentioned it yesterday. So suppose I have two intervals that sit next to each other. They can be arbitrary, but since they're all isomorphic to each other, I may as well take them to be 0, 1, and 1, 2. So the algebra corresponding to this one is a subalgebra of the whole thing, and the algebra corresponding to that one is also a subalgebra. These subalgebras are supposed to commute and generate in a topological sense. If these intervals have a little gap between them, then there's something stronger that one can say. So, well, things that commute and generate, what do they generate? They generate a copy of the algebraic tensor product. The algebraic tensor product has a canonical completion in the world of Von-Neumann algebras. And you might ask, well, does this always extend to that completion? And the answer is no if the intervals touch, and yes if the intervals have a gap. So you need to put this as an axiom when the intervals have a gap. There was also a question yesterday about if you move things a little bit, so if you move the embedding a bit, do you get homomorphisms that are related in some way? And I said, yes, they're conjugate. So this is an axiom that says that. So this is the group of diffeomorphisms of an interval that are the identity near the boundary. And I may as well take that interval to be 0, 3 and claim that it's the identity on 0, 1 and the identity on 2, 3. But that's sort of an arbitrary choice. Well, such diffeomorphism induce automorphisms that are inner. And then finally, there is a last axiom which is a bit more complicated. It involves this non-commutative L2 space of a Von-Neumann algebra. And well, I won't comment on it. I won't really use it, but it's there. So this is my working definition. So now there's a subtle point, which is that conformal nets have two roles in life. One of them is to be a model for chiral conformal field theory. And now you might tell me there's nothing in common between this slide and the previous slide. And I claim that both of them somehow model chiral conformal field theory. And yeah, I have nothing to say about it right now. I mean, I can elaborate. It would take some time, but it is possible, given one of the definitions, to try to make an attempt at capturing the other one and vice versa. But anyways, this is what I take as my beginning point. So one of the roles for conformal nets is to be models for chiral conformal field theory, and another role is to be a model for three-dimensional topological quantum field theory. And actually, there's a slight difference between these two notions of conformal nets. And conformal nets, as axiomatized in this slide, are the ones that I believe correspond to 3D TQFTs. The ones that correspond to two-dimensional conformal field theories, well, you need to add a few more constraints. There's more conformal nets corresponding to 3D TQFTs than ones corresponding to 2D chiral conformal field theories. The extra constraint, roughly speaking, is a constraint about this arrow here satisfying some kind of positive energy condition. This homomorphism from the diffeomorphisms into this group of operators. If you look at a vector field that goes only one direction, you want it to correspond to a positive operator there. But in general, this definition does not impose that condition. So I repeat, you have chiral conformal field theories, and these sit as a subset of 3D TQFTs. The ones that I've been talking about before, namely the ones coming from loop groups, these do satisfy this positive energy condition, and therefore associated to a loop group on a level, there is both a chiral conformal field theory and a 3D TQFT associated. But that's sort of philosophy. I mean, that's just to know where we're going, but it doesn't really matter. I mean, I'm going to do a construction, and I'm going to use this. So the guiding plan is to try to take this picture and give a meaning to that picture using conformal nets. For example, if I want to say what is the algebra associated to a point by the full CFT, well, so here's a point. So what are we supposed to do? We're taking a thing which is of dimension either 0, 1, or 2, and we're supposed to cross it with 0, 1. So let's cross it with 0, 1. And then we're supposed to read off from this picture what we have to do. So what I see here, I see an interval with a little something in the middle. So I can already tell you what. So there's a special case for which I can already tell you what the answer is, which is the case when Q the unit object is always a Frobenius algebra. And that corresponds to when this defect is absent from the picture. So that's called a Cardi case. So when this defect is absent from the picture, well, what do we have? We have this little red interval, and we have a conformal net. And what do we want? We want a von Neumann algebra. Well, a conformal net does exactly that. It produces a von Neumann algebra. So I have told you already in the Cardi case what is the von Neumann algebra associated to a point. It is the value of the conformal net on the interval 0, 1. Now I want to do the same thing in the presence of a defect. Well, what is a defect? So I need to tell you what the defect is for a conformal net. So the notion of defect is a bit analogous to the notion of a bimodule. So a bimodule, you have two algebras, and there's a notion of bimodule. In conformal nets, for you have two conformal nets, and there's a notion of defect between these two conformal nets. And you could imagine coloring the top part of this picture with one conformal net and the bottom part with another one. But we're not doing that. So let me tell you now what the defect is. So we start with, here I can make this a little bit bigger, I think. We start with two conformal nets, A and B. So the first line is, the first part of this slide is just setting up some terminology for and the definition only starts really here. So a defect is going to be a functor from a category of bicolored intervals to the category of Von-Neumann algebras. What is a bicolored interval? Well, a bicolored interval is an interval, meaning one manifold that's contractible. I think that's diffeomorphic to 0, 1. Equipped with a bicoloring. And a bicoloring is, a decomposition of this manifold into two pieces of two colors. So say my colors are red and blue, then a bicolored interval is either all blue or all red or half blue, half red. It's one of those three cases. One of those three cases. That's what a bicolored interval is. And the category of bicolored intervals is, well, those guys and maps that preserve the color. Embeddings that are color preserving. Not quite. There's also a little local coordinate around this point. So, okay, in those two cases, then I told you everything. Here, there's also a little local coordinate. And I want embeddings to preserve that. And also, the embeddings are not allowed to stop exactly at that point. They need to either go over it or stop before it with some positive distance. Let's see. So, if I have a functor from the category of bicolored intervals into Von Neumann algebras, I can restrict it to the category of intervals that are entirely blue. And that should be the conformal net A, say. Or I can restrict it to the subcategory of intervals that are entirely red, and that should be the conformal net B. And what the defect does, the additional data that the defect provides, is it provides values for these guys. It says, what is the Von Neumann algebra associated with one of these guys? And because all these intervals are isomorphic to each other, you could rephrase the definition by saying that a defect is the choice of one Von Neumann algebra equipped with a whole bunch of compatibilities between it and the two conformal nets. That's one possible approach. But I prefer this one where that gives you values for everything. Let me bring the slide a little bit higher so that you see the bottom. So just as before, there's orientations on these intervals, and we're looking at embeddings that are compatible with colors and with the local coordinates. If the embedding is orientation preserving, it's a homomorphism. If it's orientation reversing, it's an anti-homomorphism. And this is what I just said about the restriction of D to things that are entirely blue being the value of A. The restriction of D to things that are entirely red is the value of B. And then there's a couple of axioms. And these axioms follow really word for word the axioms for conformal nets. If I have, say, an interval which I'm going to think of as being the union of two intervals, this one and that one. So I have an algebra corresponding to this half and an algebra corresponding to that half. And those two sit as subalgebras of the algebra corresponding to the whole thing. Then these two algebras should commute, and they should generate something dense. What are the other axioms? The thing with if there's a little gap here, an actual gap, then these algebras not only commute, but generate you get the right completion. You get the completion which is the canonical completion of the tensor product. And then there are some other conditions that are actually consequences of, I mean, if you copy the axioms of conformal net, some of them are actually consequences, and so you don't need to repeat them as axioms, but they're still true. So that's a defect. The value of the full CFT on a point is going to be the value of this functor on the slide on the interval 0, 1 with its defect point in the middle. Yeah, that's it. Any questions? So the next thing that I'm going to do is I'm going to take as input a conformal net and a Frobenius algebra object in the category associated to the conformal net, and I'm going to construct a defect in that sense. That's going to tell us what to do for points. And then we're going to do something for intervals.
Right, well, next talk will be 3:30, right? But there's an informal session, so 2:30 as usual upstairs, so we have a lighter program.